Okay, hi. So this lecture, the third and last on dot product and length, is really actually this is also covers 1, 3. This is sort of hooking the first two sections back together. So if I have a matrix, uh, I have a rectangular array of numbers. So we will define a matrix to be a rectangular array of numbers, and we'll just do this. You have other sources to see too. We'll just do this by an example. So here's an example of a matrix, 1, 0, 1, 1, 4, 3. So I can look at this as columns like vectors, a sequence of vector, ordered set of vectors, okay? So this has dimension. A is 3 by 2, and this means rows by columns. It has 2 columns, so the columns are vectors. One, 0, 1, 1, 4, 3. Now the span of the columns of A is called the range of A, or the column space of A. Okay, so all linear combinations of the columns. Matrix vector multiplication. Okay, so we need, if we're going to multiply on the right, a matrix A on the right by X, X has to have the number of elements that A has as columns. So if A is m by n, then X is in, so A m by n implies X is in Rn. Okay, now, what is AX? So let's go to an example. So for example, suppose we take 1, 0, 1. We take our example 1, 4, 3. And I said X has to then be in R2. So we have X1, X2 here. Well, this is just a linear combination of the columns. So this is in the span. This product is in the span of A, and it's given by this, X1. Okay, this vector stores the coefficients of the linear combination, okay? Okay. All right. So this gives you some idea why perhaps the span is called range. Because if I look at AX as a function, transformation, I'm putting in X, I get out something. So I get something in the range of the function. Okay, for any X I put in, I get something out that's in the range. And I can think of these as constants. They sort of define the function. And the X's are allowed to wander all over the real numbers. Okay? All right, very good. We're almost to the point where we start chapter 2 on linear systems. Let me just have you practice a little with this. So let's see. So, yes, so key idea. Do I want to have you practice? Let's say, okay, yeah, let's do a quick practice example. So practice, compute. I'm just going to keep it this dimension, but it can be any 2 positive integers. So compute 1, 2, 0, minus 1, 0, minus 1, and let's put in here 1, 2. Okay, well, this is equal to 1 times 1, 2, 0, and 2 minus 1, 0, minus 1. I take this linear combination and I get minus 1, 2, minus 2. Okay, so minus 1, 2, minus 2 is in this, must be in the span of these two vectors. Okay? Okay. Well, so what, right? So what? Why do we care? So we can conclude from this, let's just write this down. So we conclude minus 1, 2, minus 2 is in the span of, is in the column space of this matrix. 1, 2, 0, minus 1, 0, minus 1, which is the span of these two vectors, okay? Well, what that tells me is that a certain system of equations has a solution, okay? So this is the key. So this tells me that the following system of equations has a solution. Okay. 1, 2, 0, minus 1, 0, minus 1 equals minus 1, the one I found, 2, minus 1, has a solution. Obviously, we know what it is because we put in 1, 2 over here. It's 1, 2. But say I didn't start here and I just gave you this and I said this was in the span of these. Then you know it has a solution. Okay? So, why? This is because since this is in the span of this, because this means there is x1 and x2, so that x1, 1, 2, 0, okay, almost there. Now, to go from here, I just want you to see what other form does this have. This is a matrix equation. This is a matrix equation. This is AX equals B. I can think of this as AX equals B. And I might want to solve for X. I know the answer already. It's 1, 2. But maybe I put something else in here. So if I ask you, so question, does AX equal, let me say I put something else in, 5, 1, say 5, 12, 1, have a solution. Well, another way to say that is, alternate way to say it, alternate question, is 5, 12, 1 in the column space, in the span, column space of 1, 2, 0, minus 1, 0, minus 1. So is it in the span there? Well, we haven't made any progress towards answering it, but we found a different way to say it. That's it so far. We might know ahead of time it is or isn't, and then we maybe don't even need to know what the coefficients are. We just want to know if it has a solution. Okay, well, maybe just as a last thing here for this problem is to see that these can be written without matrices too, just as what's called a linear system. Although the compression that the matrix equation gives us here, AX, 3AX equals B over 3 equations, is part of the reason for linear algebra. So let's just see these, note well, these matrix equations can be written as a set of scalar equations. For example, minus 1, 2, 0, minus 1, 0, minus 1, x1, x2 equals 5, 12, 1. What would happen to this? Well, let's see. I have x1 minus 1, 2, 0 plus x2 minus, oh, should that be, that should be plus 1. Sorry, just want to keep it the same. Okay, minus 1, 0, minus 1 equals 5, 12, 1. Well, first of all, you can see over here I get a vector in R3, and here I have a vector in R3. They're equal if every element is equal. Two vectors are equal only if every element are equal. I can't have one that's not. So I now can put these together. I have x1 minus x2. Here I have 2x1, and here I have minus x2. So you see the equations, right? Now it's just formality to write this without the brackets around it. You can also see if it is in the span. I can check here. X2 must be minus 1. X1 must be 6. So I have 6 minus a minus 1. That's 7. So we see our answer. No solution. So this implies 5, 12, 1 is not, right? Is not in the column space. It's not in the span of 1, 2, 0. Minus 1, 0, minus 1. Okay, that's it for chapter 1. We start with chapter 2 with the next set of videos. 1.3 is pretty short here on matrices. I'm going to upload these now. See you tomorrow.